Today we're going to focus on intrinsic electron magnetic moment derivation. This paper was first published in 2015. The Bohr magneton mu sub b and hence the electron intrinsic magnetic moment mu sub s without G factor or electron rest mass consideration and without anomalous magnetic moment quote unquote correction may be calculated from the fundamental length d and time t constants of binary mechanics. In this report, mu sub s is computed from dt and elementary charge E and a classical expression of magnetic dipole moment based on a current around the perimeter of a circular area, marking perhaps the first direct derivation of mu sub s from first principles of a comprehensive physical theory. The more conservative interpretation is that the so-called anomalous magnetic moment represents an experimental artifact with reference to mu sub s measurement. Here's the electron spot showing the negatively charged m bits as white circles, which form a plane around a central axis, the gray circle, which is orthogonal to the page plane. Here we got the electron spot based on a physical interpretation of binary mechanical space. By assumption, the one state m bits, the white circles, are located at the center of their size d cube bit loci within each of the three spot units. With repeated application of the unconditional and strong bit operations, a one state m or mite bit will rotate counterclockwise around the spin axis shown as the gray circle, orthogonal to the plane defined by the mite bit loci. The spin radius r is the square root of 2/3 times d, where d is the bit locus cube size and fundamental length constant, proposed to equal about 2/3 of a femtometer. The negatively charged one-state mite bit centers are assumed to define a circle on their spin plane with area equal to pi times r squared, which gives you this value in square meters. For the circular current, we try electric charge, E, divided by pi times T. And we get so many, looks like 9 million or plus amperes, where E is elementary charge and T is the binary mechanical time tick constant in what at that time I was calling observational space, and the reference indicates that this T constant here is actually the primary time constant T times alpha. Combining equations 1 and 2, we have the magnetic moment equal to the product of A amperes times the current, which is going to give you 9.2 to the minus 24 joules divided by Tesla. The area A and circular current components in equation 3 may be simplified as shown here. This computed theoretically derived value for mu sub s in equation 5 is equal to mu sub b, the Bohr magneton, within several parts in a billion, as shown in equation 6. Note that none of the computed values above can have a precision greater than the codata constants used in this paper or for D and T in a previous report. Back to our physical constants derivation tree, we can see that the intrinsic electron magnetic moment was derived from elementary charge, the arrow right here, derived previously, length, the arrow coming all the way down, and the time constant coming all the way down, and alpha. Look, Ma, no G factor. The present report derives electron magnetic moment, mu sub s, from elementary charge E, Bm fundamental length constant, D and T, alpha, the fine structure constant, which was included in the T constant above, and a classical expression for magnetic moment. A typical expression in physics literature requires electron rest mass me, such as the Bohr magneton. Not now. Here we have the Bohr magneton expressed in terms of elementary charge E, the reduced Planck constant, and the mass of the electron. Notice this is an equation showing relationships among measured values. It is not, underscore not please, a derivation of an observed value, the Bohr magneton, based upon first principles only. No measured values allowed. Also, conventional conceptions use the Bohr magneton and a so-called gyromagnetic or G factor. Not anymore. This work may represent the first accurate derivation of electron magnetic moment from first principles of a comprehensive fundamental physical theory. G factor, the nail in the coffin edition. Can you hear the spooky music? In the present context, the need to invoke a G-factor correction in particle magnetic moment work is clearly, what? An admission of inadequate theory, no doubt due to the assumption, which is obsolete, of continuous space-time. The electron G-factor of about 2 is typically attributed to the Dirac equation. Perhaps coincidentally, binary mechanics was developed from a pair of relativistic Dirac-Spinner equations of opposite-handedness. With this report, mu sub s is obtained directly from elementary charge E and a quantized spatial unit. Now, we previously derived elementary charge E in another paper, so that's not a measured value. It was derived from primary constants right here, without an intermediate step requiring a G factor value or indeed explicit reference to the Bohr magneton at all. An intrinsic electron angular momentum. Meanwhile, the experimentalists are stars in the current show, providing precision measurements of magnetic moments for many particles. The current work may suggest to experimentalists that the G-factor nonsense should be dropped, bang, on the floor, by reporting the results directly as, say, joules divided by Tesla. The so-called anomalous magnetic moment. Think about it. A Nobel Prize was given for this. The present derivation does not account for the anomalous magnetic moment correction based on experimental measurements of mu sub s slightly larger than the accepted Bohr magneton values. Further analysis might reveal that this correction is due to the potentials which one state electron M and L bits, called mites and lights, represent. Okay? Not only are they constituents of the electron bit cycling, allowing us to calculate the magnetic moment, but also the M bits are part of the electrostatic potential, and the L bits, lights, are part of the magnetic potential. First, a one-state M bit is always part of the larger electric potential field, as I just said. Specifically, in the scalar bit operation, this potential can accelerate a one-state M bit in a concurrent spot unit in a different spot adjacent to the one-state mite in the electron spot. Okay? So you see how your experimental measurement setup can be affected by the fact that the intrinsic constituents of the electron themselves comprise, at different points in time, electrostatic and or magnetic potentials when in the L-bit position within the electron spot. Second, in the 3 simulator tick electron bit cycle, the one-state lights, or L bits, occur and can accelerate one-state M bits, or mites, in adjacent countercurrent spot units during the vector bit operation time tick t. In short, the bit cycling producing the magnetic moment of the electron can, and most probably does, affect bit motion in neighboring spot units. These sorts of events, think about it, may account for the small anomalous magnetic moment, quote-unquote, correction. If so, it may come down to a matter of judgment in the physics community whether the anomalous magnetic moment should be treated as an unavoidable experimental artifact. Quantum electrodynamics, with use of Feynman diagrams, purports to calculate the electron anomalous magnetic moment with stunning accuracy. It might now seem strange that this considerable effort might have targeted nothing more than an experimental artifact. Bong. This is primarily of historical interest since QED has been upgraded to binary mechanics as briefly outlined above per relevant underlying anomalous magnetic moment mechanism. Our spokesman for this week is Lulu, who sings If I Were You. These are probably the most clever lyrics ever written in a popular song. And of course, she's talking directly to theoretical physicists.